All right, let's start our discussion with the gradient, and this discussion will motivate. I'll edit it out. No, don't worry. Let's start our discussion with the gradient, and this discussion will motivate a few very interesting questions that will lead to our discussion of the covariant basis, coordinate basis, and then change of variables, and that will give us an excuse to introduce the tensor notation. So what is the gradient? You are familiar with two definitions of the gradient. One is that it's the vector that points in the direction of the greatest increase of the function, and its magnitude equals the rate of the increase of the function. And another definition that you know is that it's a pair of partial derivatives. So assuming this is in Cartesian coordinates, we'll see the problem with this, and we'll be on a serious quest to rid ourselves of Cartesian coordinates. There's something very nice about the first definition that I gave, and it's the fact that it can be implemented without the use of any coordinates. So you imagine the temperature in this room as your function, and it's defined at each point in space. And it's always very useful in these problems to think about the domain of the definition of the function. Don't think about its graph, because I think it's confusing. When you think about the graph of a function, you think about its domain, but also where the values of the function live. And that makes for a confusing geometric picture, because most of the action actually happens in the domain. So all you have to do is imagine the domain, and most of the interesting vectors, including the gradient, live in the domain. So if we imagine this room to be our domain, or on the board we'll have a two-dimensional example, you can sort of measure the gradient by picking a point and then maybe sampling all of the surrounding points and finding the point where the increase in temperature is the greatest, calculating the rate of change, and maybe that's your good candidate for the gradient. It's an arrow that points in the direction of greatest increase, and its length equals the rate of increase. So it's a complete definition of the vector. And then you would find points closer and closer and closer. You would basically do this sort of sampling on a sphere that gets smaller and smaller and smaller. So it's some kind of limit is implied here. And then for each sphere, as they're getting smaller, you will find the point where the temperature is the highest compared to the center of the sphere. And you'll say that's the direction of the greatest increase. And by dividing by the distance to that point, you'll figure out the rate. And by taking this to the limit, conceptually, you will be able to determine the gradient, which is an arrow. So this definition is beautiful in that it's geometric. It does not require the use of any coordinates in order to determine the vector. This definition, when you define the gradient as a pair of numbers, pair of partial derivatives, well, there's a problem right there. So what is it? Is it a pair of numbers, or is it a vector? Or in three dimensions, is it a triplet of numbers, or is it a vector? How do you connect the two? That's question number one. Question number two, of course, is how would you define it in other coordinate systems? We'll attempt to define it in the Cartesian coordinate system, and you will actually see that our naive attempt at defining the gradient, in other words, connecting these numbers to the arrow, in the Cartesian coordinate systems will fail. But supposing we fix that, how do we expand that definition to other coordinates, like polar coordinates or spherical coordinates, or any other arbitrary coordinate systems that you might find convenient for the purposes of solving your problem? So let's try, at first naively, I'll take suggestions, to connect this arrow, which we just described, that flies know how to measure, because flies can go, well, maybe they can measure the gradient of brightness. That's how they find the window. Or maybe it's actually the gradient of temperature that they follow. Right? If a fly or a bee wants to get out of the room, it goes straight towards the window. Well, maybe it sees the light and goes that way. But suppose it's a temperature sensing mechanism. It could still find its way towards the window. It would just go in the direction of greatest temperature decrease, opposite of the gradient. So that invariant arrow, so that definition is invariant. And there's a word that's even stronger than invariant, and that's geometric. We'll use the word invariant to mean that it evaluates to the same number in all coordinate systems, so it doesn't vary with coordinates. But this definition that we gave first, it's not even invariant, it's geometric. It doesn't even use coordinates. And the question is, it doesn't use coordinates, but how do you express it in a particular coordinate system? Our quest is to combine the power of coordinate systems with our geometric intuition. So that arrow will denote by this symbol. Maybe just once in this course. We'll go away from this notation. There's better notation for this. So here's the arrow. We just described it. And here's a pair of numbers. And you have to somehow connect them. Any suggestions for some expression? Let's say this is happening in Cartesian coordinates. I'll draw my... Remember what Cartesian coordinates are? This is our unit. Cartesian coordinates is an orthogonal coordinate system where the coordinate lines are 1 unit apart. So this is Cartesian coordinates. If I made these spaced twice as far, it would no longer be called a Cartesian coordinate system. We might call it the stretched Cartesian coordinate system. So here's our Cartesian coordinate system. The coordinate lines are 1 unit apart. I can probably not make a better drawing. So we'll try to hold on to it for as long as we can. And so now that you have a Cartesian coordinate system, a function such as temperature becomes a function of x and y. Until we have coordinates, we just have a point, and at that point we can tell you the value of the function f. That's all we can do. With a coordinate system, f becomes not just a function of the points in space, but a function of x and y. And it would even be much smarter, I think, to use a different letter to denote this, because these are two different things. This is f as described geometrically, a function of point in space. This f is a function of two variables, such as x squared minus y squared. With this function, you can do invariant things, for example, evaluate the gradient. With this function, you can do analytical things, such as evaluate partial derivatives. And the question is, how would you connect? Can you give me an expression using these guys and maybe something else? Well, I'll tell you what else you might want to use. These are called coordinate vectors. I with a little arrow and j. All right, now you have to tell me.
So
go for it.
1 over the square root of the dot
product
of y with itself.
Okay, well, what you're telling me is wrong anyway.
Okay.
But I can see where you're going with it. So give me the naive thing you might think. The naive thing is...
Make the partials the components of the vector?
That's right.
Yeah.
So that's right. That's what you would say. df. Are you saying what you're saying because you read the first chapter of the book? Or you thought about this before?
Because I read the first chapter of the book.
This will actually be a little bit of a wake-up call. And there's a typo in the book. I discovered it this morning. There shouldn't be any square roots, and that formula is missing other things. It's not good. The next edition will have to fix it. Okay. Plus df dy, df dy, j. This is definitely a step in the right direction because it takes a geometric concept and finds a algebraic or maybe analytical expression for it. That's a good step towards marrying algebra with geometry, towards letting them lend their mutual forces to each other. That's Lagrange's quote. A very good step in that direction. But is this done correctly? This question, even though it's nice in the sense that it connected a geometric concept with algebraic expressions, begs two important questions. Number one, what would you do in a polar coordinate system? In the polar coordinate system, f, and ideally you would use a third letter, but nobody does that because you would run out of letters. So we'd use the same letter f, but it'll be a function of r and theta. So the only tools at your disposal then would be df dr, df d theta. What are your I and j for polar coordinates? So we'll define that in just a very short time. But that would be the question number one. How would you, okay, so we did it in Cartesian coordinates. What would you do for other coordinate systems? So we need to find a way to define these coordinate vectors. So that's number one. Number two, if we naively wrote the same formula, somehow defined coordinate vectors and wrote df dr times the vector corresponding to the r variable plus df dy, the vector corresponding to the theta variable, and then evaluated the expression, would you get the same error? Would you get the same error? That's the most important question. They're equally important, but that's an important question as well. Let's try to answer that question, because even with orthogonal coordinate systems, orthogonal affine coordinate systems, which means coordinate lines are straight lines, you can ask the question, what would happen if we stretched the Cartesian coordinate system? It would no longer be called a Cartesian coordinate system, it would be called stretched Cartesian coordinates. And they might look something like this. Let's say the coordinate lines are two physical units apart. Two physical units apart. So our coordinate system, our alternative coordinate system, will look like this. That's good. That's good. That's good. And one more. It's not that. Okay. So this point in the old coordinates had coordinates 0, 0. And in the new coordinates, it also has coordinates 0, 0. This point in the old coordinates had coordinates 1, 0. And in the new coordinates, it's 1/2, 0. One more point. Let's look at one point. This one. In the old coordinate system, it was 0.22. In the new coordinate system, it was 0.11. Okay. These new coordinates, we'll use prime to denote them. It'll be f. It's kind of bad to use the same letter f. Let's use letter f prime, because it's a different function of x prime and y prime. You did, on one of your homework exercises, you did this sort of substitution and you figured out what this new function is. It's a matter of plugging 2x for x, or maybe 2x prime for x, or maybe 1/2 x prime. Hard to do it quickly. And let's write down the same definition, the same sort of expression, but in this new coordinate system, and talk about whether we'll get the same vector or not. Who thinks we'll get the same vector? Who thinks we'll get a different vector? Who would have thought that they would get the same vector before they read chapter 1 of the book? Who would have guessed that? Yeah, that's what I would have guessed too. So it was a little bit of a wake-up call when you realize that you don't get the same thing. So let's realize that together. So another attempt, and would these two be the same, would be df prime, a new function. Easy to relate to f, but it is a new function. df dx prime, I prime, plus df prime, dy prime, j prime. And let's think about what happens to I, how is I related to I prime, and j related to j prime. Well, for I and I prime, we have no choice but to define them, let's do it at this point, this way. This is I prime, and this is j prime. And they're just points that go from one coordinate line, vectors that go from one coordinate line to the next. That's the only way you have of defining vectors I and j, or in this case I prime and j prime. So they double. That's very clear. When you stretch the coordinate system by a factor of 2, the coordinate vectors double. That's good. So this part, these guys double. What about these partial derivatives, the new ones compared to the old ones? Do they double or do they halve? Not easy to answer this question quickly, but let's just think about it together. What this is, what the derivative is changing x the independent variable by a little bit, delta x, like 0.1, and then dividing the corresponding change in the function by delta x prime. So dividing the change that corresponds to the change of 0.1 in the variable by 0.1. And here it's the same thing, except it's the change of 0.1 in x and the corresponding change in f. And then you do this for 0.1, 0.01, and take it to the limit and see what happens in the limit. But let's look for a final delta x. Let's change delta x by 0.1 and see where we end up. So if we start at this point, and we change, and we look at the function in the old coordinates, and we change delta x by 0.1, we would probably be white chalk because it's all coordinates here. And you would compare the value of the temperature here to the value of the temperature here. Subtract them, that's the difference divided by 0.1. And remember, so these functions change from one coordinate to another, but they both come from the same invariant function, temperature, that's just defined at a point in space before the coordinate system was ever introduced. That's the values that we read off. We don't even care what expressions these are. We can just look and say, oh, here's the value, by just putting the thermometer there. That's the invariant way of reading the temperature. Put a thermometer there, as opposed to evaluate something like x squared minus y squared. Now, let's, by the same token, change x prime by 0.1. Well, changing x prime by 0.1 lands you here. That's, excuse me, not x1, x prime. This is x prime equals 0.1. This is x equals 0.1. This is x prime equals 0.1. It's twice as far. It's twice as big a step. So in the linear sense, the temperature will change twice as much when you take the same step in x prime as opposed to x. So f prime as a function of x changes twice as fast as f as a function of x. Let me repeat it correctly. F prime as a function of x prime changes twice as fast as f as a function of x. So this derivative is double this derivative. So this vector is double this vector. And this number is double this number. So this expression in the new coordinate system will be 4 times as large. So it's a failure of our trying to express a geometric concept in analytical terms. This works in Cartesian coordinate systems. It's actually not at all obvious. One of the exercises deals with this. Because Cartesian coordinate systems can be shifted and turned. It's a family with 3 degrees of freedom. So it's not at all, so i's will change, this function will change completely when you rotate the Cartesian coordinate system. But you can one of the exercises actually asks you to prove that if you evaluate this very expression in any Cartesian coordinate system, then it works. But in any other coordinate system, like stretch Cartesian coordinate system, it fails. And in polar coordinate systems, we don't even know how to define this. But in any case, before we go to a more complicated coordinate system, we've got to fix this. This is not the right expression for the gradient. So maybe we have to give up on this being the definition of the gradient. Right? It's a big problem. Right? It is a big problem. So if you've always casually thought that this pair of partial derivatives is the gradient, right, then this is a real cold shower, because the expression that you would think matches you up with the vector gradient, invariant gradient, geometric gradient, doesn't work. It comes 4 times as much. So let's think about how it, yes?
Why did you say in the linear sense?
Because when you're talking about, so you have to be careful because temperature is not a linear function. I cannot really say that the difference in temperature between these 2 points is twice than the difference. That would be a wrong, for me to say the difference in temperature between these points equals double the difference in temperature at this point would be an incorrect statement. For me to say approximately is not fun. You don't want to say approximately. So I was basically going after the statement that this derivative is twice this derivative. So the way mathematicians say it is the linear part of this difference is twice the linear part of this difference. That's just saying that in the limit, as these points get closer and closer to this one, the ratio will be getting closer and closer to 2. So math in calculus, it's very common to say in the linearized sense, or in, linear changes. Okay, so how would we change the expression to at least make it work for all the stretched coordinate systems? Does anybody remember from reading chapter 1, or?
Does it normalize it with respect to the vector?
You have to scale down the unit vector.
So let's take down, so that's works half of the way. So suppose we use this rule. Right, that's what you're saying. Take the normal. Take the normal. Well, let's see. What would happen when you go from one coordinate system to the other? So let me point out what's good about this expression. What's good about this expression is that it's given in terms of things that are available for any affine orthogonal coordinate system. Every object is intrinsic to the coordinate system in the space. That's nice. There's no background coordinate system, in other words. But let's see what happens when you go from white to yellow. This will remain the same, right? Because it'll still be the unit vector in that direction. So it would just take the vector I prime and divide it by 2, and look, it's the same as I. So that's good. That would not change from stretching coordinate systems. What about df dx going to df prime dx prime? That will still double. So this expression, as you go from white to yellow, will still double. So not quite. So that's not quite the fix. A small change.
Square the denominator.
Yeah, square the denominator. There you go. That works. Now do you see what happens when you go from white to yellow? This doubles. This doubles. This, the bottom quadruples. So 2 times 2 divided by 4, we're good. So, oh yeah, I just squared it already. So that's actually a fix. So that actually saves the concept of the gradient, at least for Cartesian coordinate systems and stretched Cartesian coordinate systems. They don't even have to be stretched equally. It can be stretched by one factor in this direction and by another factor in this direction. But what about polar coordinates? What about polar coordinates? How do we define an equivalent of this? So we're going to do that almost next. Before, I want to go back and talk about this expression a little bit and ask analytically, well, why does this deserve to be called the direction of greatest increase? And this will be a very nice exercise. We'll do it first in Cartesian coordinates, which will soon become a no-no in this course. We'll try to not do anything in Cartesian coordinate system if the question is general. This is a general question. Why does the gradient correspond to the direction of greatest increase? It's a general question that should not be asked with the help of a Cartesian coordinate system. But let's, for the sake of practicing differentiation and just answering this question, use a Cartesian coordinate system. And then we'll talk about expanding these kinds of expressions to arbitrary coordinates.
What if you skewed it?
Yeah.
I never got into
Oh,
that
that's a
before.
fantastic question. If you really considered, sometimes I call it the Helsinki coordinate system. You mean this, right?
No, like if you had like a parallelogram instead of.
Yeah, that's what I kind of drew.
Oh, okay, yeah.
Yeah. Just not exaggerated enough for your taste. There you go. Like this? Yeah, it would absolutely fail. It
And is
would
there a
totally
fix for
fail.
it, or
I'm sorry?
Can you compensate for it? Or
Yes, you can. That's tensor calculus. How to compensate for it. Except it's asked in a prettier way. Yes, we'll answer that question relatively soon. Yeah, that's the challenge. I'm very glad you brought this up. This sort of expression would completely fail. The definition of I and j, I don't know anymore what's my coordinate system here, but would be this. Those are your I and j. So for these coordinate systems called affine coordinate system, I call it the Helsinki coordinate system because if you look at the map of Helsinki, it's sort of like Manhattan, except it's not at the right angles. It's a grid, but it's a skewed grid. So that's kind of nice. Yeah, it would totally fail. So we have to find a way that it works. We have to find an expression that works in all coordinate systems. That's the challenge. And if you have an expression that works in all coordinate systems, that expression has geometric meaning because you've removed all of the artifacts of the coordinate system because you have an expression that works in all coordinate systems. So it effectively uses the power of coordinate systems but doesn't impose any artifacts of a particular coordinate systems on it. Okay, let's pick a point and let's find its derivative in this direction. Let's find its directional derivative in this direction. Let's call it the vector n, which equals n1 I plus n2 j, so we might as well write it like this. We're in Cartesian coordinate systems. It's like going on a diet, which I can relate to, and this is like your last hurrah. This is your Thanksgiving meal before you go on a diet. All right, this is our last use of the coordinate system that's uncalled for. So we're going to look for the rate of change along, the rate of increase along this direction. So for our function f, let's leave a little bit of space, f, which is a function of x and y, we have to plug in how this line is expressed in terms of arc length. Because the definition of the directional derivative is you go a certain physical distance in a particular direction. This would be going a unit distance. And then, of course, you find the limit as the distance traveled go to 0. And find the derivative with respect to that parameter, arc length. It's the derivative with respect to how far away you're from this point. So this line, if this is point x0, y0, then this line L, has the following equation. L, can I equal, I won't write equals, I'll write colon. x0 plus n1s, y0 plus n2s. So this works if n is the unit vector. That's the parametrization of this line. So our function, as we go away from this point of interest in this direction, can be written as x0 plus n1s, comma, y0 plus n2s. And that forms a new function. I forget what notation I used in my textbook, but we can call this f of s. And the directional derivative would then simply be df ds, because that's the rate of change of this function in this direction, characterized by the distance. So the directional derivative in this direction equals simply f prime of s. And by the chain rule, and these are the nice moments in tensor calculus and vector calculus, it's when you take the derivative and all of the important elements appear on their own. You don't force them. Everything that you need will appear on its own. This will be one of the most important, even though it's a subtle lessons. It's a very important but subtle lesson that most of the important relationships are obtained by writing down an identity in some variable and then taking the derivative of both sides. If you're not Gauss, you can derive virtually all important relationships this way. If you want to go beyond this, you have to be a little bit of Gauss. Right? But every fundamental relationship that we'll encounter in this course can be obtained by writing down an identity in a certain variable and taking the derivative of both sides. That's how every important identity will be discovered, except the concept of Gaussian curvature, which required Gauss's genius. Okay, let's use the chain rule. Very simple, it's df dx. It's f as a function of x, df dx, times dx ds. So this would be x of s, and this would be y as a function of s. So the way the chain rules is df dx. And I write f sub x a little shorter, means the same thing. This is df dx times dx ds. And tell me what dx ds is?
N1.
N1 plus df dy ds. And dy ds is? N2. And this, because we're in Cartesian coordinates, this will also require an adjustment when you go to other coordinate systems, is the dot product of what we call the analytic gradient of f and n. This is gradient of f dotted with n. It's a remarkable formula. I will explain to you in a second why I think it's remarkable and give you an explanation that shows that maybe it's not so remarkable. So what this is the directional derivative of f in the direction given by this unit vector. So it says that if f is defined in this space, and you want to find the directional derivative in this direction, better choose the unit vector. You just have to dot this unit vector with the gradient of f as defined analytically. So this, at first sight, is a little bit, seems too strong of a statement, doesn't it? Because the gradient is just two numbers. And it tells you that if you know the gradient, then you know all directional derivatives. If you know the gradient, two numbers, analytically speaking, then you know all the directional derivatives, infinitely many numbers. That's kind of amazing that it's such a simple relationship, that there isn't that much choice, that much freedom in what directional derivatives can be. If you're constructing your own crazy function, that once you've chosen what its gradient is, that pretty much dictates the rates of change in all directions. So why is this the direction of greatest increase? Well, that's because this dot product is the length of f times the length of n, which is 1, times the cosine of the angle between them.
Yeah.
Do you know how long ago?
Not too long, because it didn't go black.
Not even a minute.
So
Okay.
it didn't go black.
Okay. You think I should repeat this
Yeah.
again? Okay, let's repeat this argument. I lost my unit vector.
Just transform through the proportion.
No. Obviously, I'll edit all of this out. That's the whole point, that the space exists on its own. Should I not address your joke because you didn't mean it? Or part of you meant it? You didn't mean it. I'll take advantage of it anyway, right? The space exists without coordinate system, so the space has its unit, regardless of what coordinate system you impose. So when you impose the yellow coordinate system versus the white coordinate system, it's not like the unit changed. The unit is still the unit. The coordinates changed. The coordinate vectors changed, but the unit is still the unit. Okay, so the point we were making here, in case it got lost, is that we just figured out the directional derivative is the dot product of the gradient as defined analytically by the normal vector. By the unit vector in the direction that we're interested in. And this dot product equals the length of the gradient, which is fixed, times the length of n, which is always 1, times the cosine of the angle between them, which is the only parameter we get to play with as we choose different directions. And that parameter and the cosine of the angle is the largest when the angle is 0. So in other words, when the direction that we're interested in points in the direction of the gradient. And then the dot product equals the length of the gradient, which proves that the direction of greatest increase is the gradient, and its length equals the rate of greatest increase. Okay, so now the next step is to try to expand the expression to other coordinate systems, which is accomplished by defining a coordinate basis in arbitrary coordinate systems. We'll do it in generally and calculate it for the polar coordinate system, and then finding ways of that'll take several hours to get there, of coming up with an expression that actually works in all coordinate systems. Okay, so let's take a break here. You want to stop?